This session is about defining concentrated loads in slope W and then going on to defining and using reinforcement in slope W. We're going to start with concentrated loads and point loads. It's best illustrated with this example. We can go to File SLP 21 and we will define the surcharge load representing a pile of sand, and then secondly we will define a point load to illustrate how this is done, although point load itself is somewhat rather meaningless at this particular case. It's just intended to show the procedure. So let us go to GeoStudio and open up SLP 21. And after you have opened the file and you have gone to analysis number 1, this is what you should see. Clicking on the All Objects Zoom button. We have 3 analyses here. Number 1 is no surcharge. Number 2 has a surcharge load, and then number 3 has a surcharge and a line load. Let us analyze the first case with no surcharge just simply as a reference point. Clicking on Start, we can analyze the first case. Going to the results view, we get a factor of safety of 1.56. Now let's go back to the define view and go to the second analysis, and we want to draw a surcharge load representing a pile of sand with a unit weight of 20 kilonewtons per meter cubed. First of all, let's zoom into the area of the pile of sand. Let's turn on our snap to grid. And then we can say draw surcharge loads. We will add a load represented by line number 1. The unit weight of the material is 20 kilonewtons per meter cubed, and it acts in the vertical gravitational direction. When we click on draw, our cursor turns to a plus sign, and we can then draw a line that represents the surcharge above the green ground surface line. And we just go around the area representing the surcharge, and when we're finished we go right mouse click, and at this stage we could draw more surcharge loads at a different location, but in this illustrative case we're done. And now we see that we have a surcharge load on top of the slope. Let's now click on Solve and analyze this second analysis. We go to the results view, click on the All Objects Zoom button, and then we can zoom in on the area of the slip, and we see that we now have a factor of safety of 1.4. The factor of safety has gone down as a result of the surcharge. We can once again verify how the surcharge has been added to the analysis, and fundamentally the surcharge results in a line load on top of the slices that are under the surcharge. We'll zoom into the area of the surcharge, scrolling the drawing to the left, then saying View, Slice Information, and we see that for all the slices here that are under the surcharge, we have an extra load on top of the slice. Here's the load that represents the surcharge. The magnitude of this surcharge is simply the width of the slice times the vertical distance of the surcharge times the unit weight of the surcharge. Once again, it's always a good idea to spot check the fact that the surcharge has been applied correctly in the factor of safety calculations. Now let's go back to the define view and go to the third analysis. And we wanted the surcharge to be applied in the third case as well, so let us redraw it. Say draw surcharge loads and add number 1, which is 20. Notice that surcharge loads are unique to each analysis. And now we will zoom into this area here and apply a concentrated point load. We say draw point load. The magnitude is 100 kilonewtons, and we won't worry about typing in the direction. Let's apply the point load at this location here. It's quite arbitrary, but it's all just illustrative. We click where we want the point load applied, and then we get a rubber band. And notice as the rubber band moves that the angle changes. Now it's very difficult to get exactly 30 degrees, so we just click to make it approximately 30 degrees, and then we come up here and type in 30 degrees. Now we have defined a point load of 100 kilonewtons acting at an angle of 30 degrees from the horizontal. We can now analyze the third case. Start and solve. And now if we look at the results view, the 100 kilonewton force is applied it acts against the gravitational driving force, so the factor of safety is just slightly higher. But more importantly, once again, let's go to View Slice Information. And if we click on the slice that has the concentrated or point load, we see that the 100 kilonewtons is included in this slice and is used in the force resolution of this particular slice here. So this vector here represents the 100 kilonewton force acting at an angle of 30 degrees counterclockwise from the horizontal. So this very briefly shows how you can define surcharge loads and how you can define point loads. Even surcharge loads could be represented by a series of point loads, but the surcharge approach is generally more convenient than applying point loads. Anchors, nails, reinforcement ultimately are all point loads, so this is just an illustration of how a particular line load concentrated at a particular point can be applied in slope W. Moving on to reinforcement then, once again we have an entire chapter in the Slope W engineering book on reinforcement where we talk about anchors, nails, geofabrics, piles, dowels, and so forth. Once again, it is important to recognize that in a limit equilibrium formulation, that is, statics, all reinforcement ultimately reduces down to a concentrated line load. We have developed a user interface to define anchors, nails, and so forth. But ultimately, out of this interface and out of this information, we develop a load that is applied to the potential sliding mass. And this can be a concentrated load in one slice, or the load can be divided amongst several slices. This all seems rather simple at first, but it can be somewhat confusing due to the many variables involved, and so we will take a considerable time here to try and go through these examples very methodically, trying to explain exactly how the system works when reinforcement such as anchors and nails is applied. Here is a picture of the types of problems that we want to analyze and design. And as you can see, here is a very high wall with some concrete facing, and each anchor has a button on the face. And the whole idea is to have an anchor that holds up the wall. So fundamentally, we have a potential sliding mass. And without the anchorage, this piece of the ground would slide and fail. And so the whole idea is to apply a force on this free body diagram in order that the factor of safety is 1 or higher. Now it all boils down to two issues. There are two components. Either the bar could break, that would be one mode of failure. Alternatively, we have a grouted section, and the grouted section is designed or intended to bond the bar to the ground. It acts as a form of glue between the steel bar and the ground. And this bonding has a limited capacity. So another mode of failure might be that the force on the anchor is so high that it pulls the anchor out of the ground, so that the pull-out resistance is overcome and could be another mode of failure. So the whole objective is to see which one governs. Does the bar capacity govern, or does the bond pull-out resistance govern? And we have to decide which one is lower of the two and which one should be acting on this potential sliding mass or the free body diagram. Before we get into the actual application of anchors, bars, and so forth, it is useful to put a slope W analysis in the context of earth pressures. In order to do that, you can recall that the definitions of the active and passive earth pressure coefficients are as follows. For the active case, it's tan squared 45 minus phi divided by 2, or 1 minus sine phi divided by 1 plus sine phi. For the passive case, these are the values. Now these values are for the very simple case when there is no shear on the face of the active and passive wedges. It's a very simplistic case, but nonetheless quite illustrative. If we look at the case of 30 degrees, then sine 30 is equal to 0.5. And if we substitute into this equation here 0.5, we have 0.5 divided by 1.5 is equal to 1/3 is equal to 0.334 for the active case. For the passive case, we have 1.5 divided by 0.5 is equal to 3. So if we have a wall a wall that is 10 meters high, and we have an active pressure, then the resultant of the pressure turns out to be the active force, which is gamma h squared divided by 2 times Ka is equal to, say, 20 kilonewtons per meter cubed times 10 squared divided by 2 times a third is equal to 334 kilonewtons. For the passive case, we would have 20 times h 10 squared divided by 2 times 3 results in 3,000 kilonewtons. So this from the traditional theory of active and passive earth pressures for a very simple case. The question now is, how does this fit into a slope W analysis? We can illustrate this with this example in file SLP 20. And so the question is, if we apply a line load here in slope W, what will be the factor of safety? In the previous slide, we already had demonstrated that we had a force of active equal to 334, and for the passive case, we had 3,000 kilonewtons. What is the factor of safety in slope if we apply these forces? The height here is 10 meters. And we have applied the line load here at 1/3 the height. So let us see what happens when we apply these line loads in slope W. So let us then go to GeoStudio and open up SLP 22. And after you have opened the file, you should see a diagram like this. Notice that in our analysis tree we have two analyses. One is the active case and one is the passive case. Let's look at the active case first and zoom into the area of interest here. And if we go key in point loads, notice that we have applied a point load here of 334 kilonewtons at a height of at an elevation rather of 13.33 meters, meaning 1/3 the height of the wall. We can now analyze this case and compute the factor of safety. And the question is, what is the factor of safety when we apply this line load that is equivalent to the active earth pressure? And as it turns out, and it rightly should be, the factor of safety is 1.00. In other words, in slope W, under cases like this, when we compute a factor of safety of 1.0, the reinforcement or the point load that is applied to a wall, as in this case, is equivalent to the active earth pressure case. Another thing that is of rather some interest is that this angle here is very close to 45 plus phi divided by 2. In our case, phi is 30, so it's 45 plus 15 is very close to 60 degrees. The slip surface is just slightly curved, but if we take a look at view slice information and we look at all of these slices, we see that the base angle is very close to 60 degrees. It's either just over 60 or just under 60, but on average it is extremely close to 60 degrees, and if you pace through all of these slices and watch the slice angle, you will see that it is just a little bit over 60 degrees. Eventually it's just a little bit under 60 degrees. So even in slope W, the critical slip surface that gives the lowest factor of safety is very close to the theoretical inclination of 45 plus phi divided by 2. Now let us go back to the defined view and look at our second analysis, the passive case. And before we leave this dialog box, I need to point out one particular flag. If you click on the slip surface tab, you will notice that there is a special flag here called passive mode. If the potential movement is such, right to left in this particular case, and you can think of it as the potential sliding mass moving uphill, then we need to check this particular option here, use passive mode. In order to determine the direction of movement and keep the equations consistent, there is a flag in the software that says that the y-coordinate of the enter point must be higher than the y-coordinate of the exit point. In this particular case, the y-coordinate of the enter point is lower than the y-coordinate of the exit point, and consequently the need for the extra flag indicating to the software to allow this particular case. So once again we say key in, point load, and notice that in this particular case we have applied a point load of 3,000 kilonewtons, and if we analyze this case, say yes to start, and we look at the results view, we see we again get a factor of safety of 1.0 when we apply a line load here that is representative of the passive earth pressure. Again, it is of interest to note that this angle here now is much flatter, as it should be. Now it should be 45 minus phi divided by 2 should be approximately 30 degrees. And once again, if you use the view slice information command, you will see it's a little greater than 30 degrees at the crest, a little less than 30 degrees at the toe, but on average it is extremely close to 30 degrees, which it should be. So this puts a slope W analysis in the context of earth pressure concepts. To repeat, the important observation is that the line load or the anchors or the nails, if they are such that we get a factor of safety of 1, then the reinforcement system in essence is holding back the equivalent of the active earth pressure. So we do not enter into slope W the actual earth pressure, we just apply line loads that are representative of a force, And if we get a factor of safety of 1, it is representative of perhaps the active or the passive case. Now there is one other issue that is worthwhile drawing attention to, and that is if we plot factor of safety versus some force on the wall. Here's our wall, and we have some force here. We know that when there is no force, our factor of safety is less than 1. That is why we need anchors or reinforcement. We have already determined that when the force is 334, that we get a factor of safety of 1. We have also determined that when the force is 3,000, we also get a factor of safety of 1. The question is, what happens in between? We know as the load goes up, the factor of safety increases. Well, if we were to apply a load of 400, the factor of safety would obviously be higher. 500, the factor of safety would be higher and higher and higher. There comes a point, however, where we have the resisting force divided by the activating force. And if the activating force, or in other words, is equivalent to the line load, then the bottom of the equation goes to 0, and the factor of safety tends toward infinity. Now, if we were to keep on pushing, then ultimately we would move toward the passive case, and the factor of safety would continue to decrease until we reach the actual passive case. It is this zone here that you must be careful about. It is possible that we apply a line load where the factor of safety is very high and tends towards infinity. And so we have to be somewhat careful when we apply these line loads that we don't get into this area where we get extremely high factors of safety. It is still useful to do a little bit of hand calculations to know whether you are on the active side or whether you are on the passive side. So just a little bit note of warning to avoid this area where the load is equal to the gravitational driving force and the factor of safety tends to be a very, very high number. So in summary, to repeat again, when the factor of safety is 1, the applied load is representative of the active or the passive condition. In a tie-back wall or a reinforced earth wall, for example, the reinforcement system is holding back the equivalent of the active earth pressure when the factor of safety is 1. Let us move on then to another general topic related to reinforcement, and that is, where should the reinforcement be applied and what is the effect of the inclination? To illustrate the situation, I have two cases here. I have one case where I have applied the concentrated load representing the anchor at the point where the slip surface cuts across the anchor. I have the identical case, all else being the same, except that I have applied the concentrated load representing the anchor on the face of the wall. And the question is, what is the difference between these two cases? Well, as we see, that the factor of safety for this case here, the factor of safety is 1.075, and for the other case, The other case, the factor of safety is 1.076. In other words, the two factors of safety are the same. And so the observation is that the point at which we apply these concentrated loads is not all that critical, provided that the orientation of the line loads remains the same. In this particular case, the moment arm, which is perpendicular, and the moment arm here, the moment arm is identical. And as a result, the exact position along this line and along this line, where the concentrated load is applied, is not all that important. Now, if the inclination was different, then the factor of safety would be different. But the point here is that exactly where the concentrated load representing the anchor is applied is not all that important. Another topic that comes up in reinforcement is the question: does the reinforcement reduce the driving force or gravity, or does the reinforcement increase the shearing resistance? And if you follow the literature on this subject, there are two opinions on this question, and certain people have preferences, personal preferences, in certain cases. But for us here, let us look at this in terms of the factor of safety equation. Option number 1 here, we subtract the reinforcement load from the driving force. This is option number 1, where we say that the reinforcement reduces the driving force and therefore increases the factor of safety. The second option is to say that the reinforcement gets added to the resisting forces. In other words, the reinforcement increases the shearing resistance and therefore also increases the factor of safety. Now, we don't have strong preferences on either one of these options, but it is very important to be cognizant of the fact that with option number 2, that it has an effect on the overall global factor of safety. Recall from the fundamentals in Slope W presentation that we noted that the shear strength that is mobilized is the soil strength divided by the factor of safety, or we defined the factor of safety as the number by which the soil strength must be reduced in order to get a point of limiting equilibrium. That is important, and the point here is that if we are going to do this to the soil, then we must divide the reinforcement by the same factor of safety. So the consequence is that we have a factor of safety on the active earth wedge, so to speak. We must then have the same factor of safety on the reinforcement. This is option number 2. And as noted here, the factor of safety is therefore the same for the reinforcement as for the soil for this option. And so we have to be quite careful when we select this option as to what is happening to the factor of safety and the partial factors of safety that we can specify in certain cases. We will demonstrate in just a bit how these two options are selected and how to deal with the two options in one of the examples that we will go through in just a minute. Generally, before we get into the details, we have an option that says factor of safety dependent yes. And the thinking is that for cases like geofabrics that are quite ductile, and there is some strain required to develop the resistance in the geofabric, that the strain required to develop the resistance will be the same as the rate of strain required in the active soil wedge in order to achieve the resistance. And so there are some people who, in this case, select the yes option for the yes option as to whether the factor of safety is dependent on the reinforcement. Now the thinking is, when the factor of safety dependent option is no, that we have something like a pre-stressed anchor or nail, and that the structural member is very rigid relative to the soil. So if we have a pre-stressed anchor, then the anchor has been stressed to, in essence, reduce the gravitational driving force. Now, as I have already said, we at GeoSlope don't have any recommendations as to which one you should use in certain cases. The selection, in our view, is based more on intuition than on theory. However, the point is that either option is available for all types of reinforcements. We have set certain defaults for certain cases, but you can easily override these defaults. So it is up to you as the user to decide which one is appropriate for your particular situation and which one you believe to be more correct for your project. Now we need to make one more general comment about bonding and how it is specified before we move on to the detailed examples. You will find in the literature that the pull-out resistance, or the bond between the soil and the grout, is described in two different ways. One way is to describe the bond resistance per unit area. It's described as kilonewtons per meter squared. So we need to determine the area that is in contact with the soil and then multiply it by the kPa bond resistance. Another way that you will see it described in the literature is so many kilonewtons per meter of bond. And this is often what happens when we do a pull-out test. Here we have 1 meter, and the pull-out is described as so many kilonewtons per meter of bond. So we have attempted to accommodate both of these mechanisms for describing the bond resistance, and as a result, if we have the circumferential distance is pi d, if we specify the bond resistance as kPa times pi d, and we make d equal to, we make d equal to 1 over pi, which is the default, then we can say that kPa times pi times 1 over pi meters results in a resistance of kilonewtons per meter. And this is why the default diameter is 1 over pi. If you accept the default, it is not the real diameter of the grout, but if you accept the default, then you can specify the grout resistance or pull-out resistance as kilonewtons per meter. If you want to work in terms of kPa and the actual diameter, then you must specify the grout resistance as kilonewtons per meter squared. In all of our examples here, in the anchor example that we will do here shortly, we work with the default diameter of 1 over pi.